On Rome's Ciampino airfield, 970 miles from London, diplomats and air attaches saw the comet fly in at 490 miles an hour to lower the record to 2 hours and 2 minutes.
We'll talk about today, so.
A proud day for John Cat's Eyes Cunningham, de Havilland's chief test pilot. His achievement proves that jets will enable Britain's future airliners in mass production by 1953 to do twice the work in almost half the time at 4/5 the cost. Tails up for Britain. With a comet scheduled by British Overseas Airways Corporation to start the world's first jet passenger air service, Pathé News detailed cameraman Sid Baines to cover the historic trip. This is his story. A few minutes ago, I boarded the comet, together with other passengers making the trip to Johannesburg. Captain Philip Brentnell took us off with Flying Officer Charbois, known to everybody as Charlie Boy, as co-pilot. Up to 40,000 we shot to reach the comet's best operating height and headed for Rome, our first scheduled stop. Then I began to realize what a wonderful ship this was. Like all newsreel cameramen, flying is no novelty to me, but this was something new. There just wasn't any vibration. Before I'd really settled down, we were flying over the Alps. I think I got a shot of the Matterhorn over there. Skipper Brentnell pointed out Corsica, that large mass of land 70 miles away. At our great flying speed, we were soon on the last few miles to Rome. In a few minutes, Peter Panario was asking permission to land. We were over Rome. There was an hour's refueling break scheduled. I chartered a chariot for a quick look-see. I got as far as the Colosseum, where lions used to eat Christians. They tell me you ought to see it by moonlight. Unfortunately, we were due to take off at 6. As a matter of fact, I only just made it. The jets were warming up. Next stop, Beirut, Syria, then Khartoum, both of which I didn't see as we passed through during the night. But with daylight, we were headed for Uganda in East Africa. Tony Smith, our navvy, was busy. At our height and speed, calculations have to be bang on. We were looking out for Lake Victoria, the largest lake in Africa. There wasn't very much to see through the clouds, but they made a picture. I reckoned we'd done nearly 4,000 miles as I wrote up my log. Lake Victoria, on the northern end of which stands Entebbe, our next stop. Charlie Boy prepared to ease the engines to the skipper's orders, and soon we landed at Entebbe. The weather reminded me of home. One of the things that strikes you on the trip is the change in airport personnel. But the sun was smiling, like some of the local girls, when takeoff time came round, and in perfect weather we left for Livingston. Stewardess Audrey Cartmel assured us everything's fine as she served breakfast. She's always saying, everything's fine. The comet was riding as smoothly as a bird. But I soon had to get cracking again to catch the first sight of the Victoria Falls on the mighty Zambezi River, wider than Niagara and twice its drop. We were heading in for Livingston Airport now. Johnny Johnson's engines had served us well. This was the last stop before Joburg.
We'll skip a little bit.
This is the comet airliner Yoke Peter, the plane which made aviation history in May 1952, when it pioneered the world's first jet passenger service. On its first flight from London to Johannesburg, it created new records. Its performance thrilled the world and added a new chapter to the shining story of British aircraft and British airmen. Since then, the comet has blazed new trails, achieving new speeds, setting a new standard. After 12 million miles of flying, and with confidence firmly established in the comets, it was with dismay that we learned that Jupiter, the first of the comets, had crashed into the Mediterranean off Elba with the loss of 35 lives. Jupiter took off from Rome Airport on schedule. A few minutes later, the plane exploded. Ships of the Royal Navy hastened to the spot, but there were no survivors. Immediately, BOAC grounded all comets, and the search began for the wreckage. Thus, the most extensive investigation of its kind ever held was started. Naval units under the command of Admiral Earl Mountbatten gave every assistance to salvage fragments from the seabed. The pieces of the plane were taken back to Britain, and slowly Jupiter was reconstructed. And although the wreckage was scattered over a wide area,
1988, when a 737 famously lost part of its fuselage in midair. As the 737 climbs through 24,000 feet, the cabin pressurizes and the skin of the plane expands just as it's supposed to. But something else expands too, those cracks in the 737's fuselage. Suddenly, there's an explosive decompression. Its force is so powerful, a flight attendant is sucked out of the plane.
I saw what I think was the stewardess's feet as she was being sucked out of the plane. Magazines, briefcases, shoes, you name it, anything that wasn't tied down was going out that hole.
An 18-foot section of the plane is gone. Passengers sitting nearby can see the sky above and the ocean below. All that's holding the 737 together, and just barely, are the floor beams and the plane's belly structure.
About 2 rows in front of me, I could see the floor was buckling up. The plane was bending in the middle.
You can't just have a very strong piece of the bottom of the airplane without having a strong piece of the top. And so when they lost that crown, it really compromised the structural integrity.
The cockpit would move in one direction, and then finally the fuselage would actually bend and then follow.
Okay, maybe
so
get
it wasn't
rolling.
as though it was a single piece. It actually was bending. They knew they needed.
So, well, welcome to week 3. As you know, of course, there's some relevance to the things that we've been just looking at before class. So far, we talked in week 1 about fluid properties to kind of orient ourselves. In week 2, we talked about pressure at a point and how we can evaluate that. And that's really as a prelude to what we'll talk about this week, which is understanding the magnitudes of pressures applied over structures. And so we've just looked at a couple of examples of different structures, well, flight structures, both the same structures in that regard. The first for a comet, which apparently was the world's first scheduled jet airliner, which used to have this propensity not to arrive at its final destination. And people were never quite sure exactly what was going on. But it was found out that the comet, with kind of an elegant plane with these, with the wings actually containing the twin jet engines on each side, had square windows. And the square windows had stress concentrations at the corners, and the fatigue loading of going up and down, pressurizing and depressurizing, well, I guess not so much pressurizing as you go up. You have atmospheric pressure inside the plane as you take off, and the pressure outside drops, and so there's a stressing and expansion of the plane, and cracks would grow from these windows, and the planes would just break up in flight and be lost. And so that was an easy thing to remedy once you know what the problem is. But of course, forensically, you don't necessarily have the evidence to be able to do that, because it's a wreck, sometimes in the ocean, as the first crash showed there. This one, I guess, even this one's not in your lifespan. It's 87, I think. The Aloha 737 used to shuttle between the islands of Hawaiian Islands, so it used to do multiple trips a day, pressurizing and depressurizing. And this fatigue weakening, the same if you take a piece of metal and just keep on bending it until it breaks, same kind of process, in this case resulted in the roof tearing off, one person getting sucked out, but everyone else actually survived and landed on the ground just fine, which is quite an amazing story. Frightening story for those people on there, but of course much better than the the other consequences, what they could have been otherwise. We talked last time also about the Malpasset Dam, about pressures behind a thin structure, not unlike the thin structure of an airplane shell, that when it was filled, it moved the abutments and the dam itself broke. And I mentioned, but not in great detail, another event maybe that occurred a few years later in the early 1960s, the Vaillant Dam in the Italian Alps. Still stands there today, completely intact, but in that particular case, a rainstorm, there was a landslide that was sitting above the dam, and over time, with rainfall, the water level rose within the slope, and the slope slid into the dam. So like pouring a bunch of rocks, putting a brick into a bucket of water, the contents of the dam flew over the top of the dam, and there was enough volume to displace the fluid that it flooded the valley and killed 1,000 or so, a few thousand people as it went down there. I should probably find my pen, since I need to use that. Oh, all kinds of things under there. So anyway, so what we'll talk about today is pressures on structures, to try and understand a little bit about how we might move ahead to be able to define the stability of such structures. So that's the plan for today. We're at week 3. Homework 2 is live from last week. We've said before, we've been talking about pressures at a point, and we know that these main rules that we've applied so far really come from this idea that if you have in our coordinate system pressures and locations, then we know that depending on whether we have a liquid, we can kind of get something that looks like the pressure is equal to some expression like this. And if it's a compressible fluid, liquid, it might look like, it won't be straight, will it? So it might look alternatively like something like this. And we've made the point that this really comes from the observation that if you look at the shape of this curve, actually both of these curves, it's true at any particular point that the change in pressure with elevation is equal to, for the sign convention we use with negative z downwards, positive z upwards, the pressure distribution always conforms to this at a point, but depending on how the density, for instance, varies along the length of it, for a liquid it might look like this, and for that's wrong, isn't it? For a liquid it might look like this, and for gas, which is compressible, it isn't necessarily a straight line. So we can use this expression, and this is the one expression we really use to look at the behaviors today. But what we want to do is to be able to look at pressures actually applied on a structure. And so the things that we might want to understand would be, for instance, how big those forces are, how we resolve them from multiple forces into some useful force that tells us something about how they might behave. So I think in terms of the things that we're really interested in, how big are the forces? We're interested in where they act particularly. And the third thing, which isn't on here but I'll add, is what is the failure mode? Which will become clear soon enough. Okay. How do we use it to be able to say whether the dam will topple over or not? Is there a way to do it? And so these are 3 separate things that we'd like to be able to do. So maybe to illustrate it, it'll be useful just to look at this example of the comet and what that might look like. See, oh, let me do that. Whoops. See if I can move that. Does it move? No, it doesn't move. Fine. I'll just go back to doing my usual thing. So, if we take the example we just looked at, where we have inside this, don't want that, thank you, go away. Is that what I need to do now? I guess that's what I need to do, isn't it? And it gets very complicated when things don't quite work out the way you want. So, we have this aircraft fuselage, which has inside it a cabin pressure, and outside it has what is the atmospheric pressure. We said before what we think these are. This cabin pressure should be something like 100 kPa, kilopascals. We also looked at the change in pressure as you go up in the column, and we looked at 10,000 meters. The pressure was something like 20 kPa. I think we did that in, would have been last week. And so the question is, how do we resolve this to be able to say something useful about the system that we're dealing with? So what we could do is we could cut this thing in half. And I can't draw this probably very well, but that's not too bad. And we could look at the behavior of this just, again, by using kind of a free body, as we've used before. Like for the concrete form example we did with the step. So, for instance, we could look at the pressures which are being applied inside the cabin. And this is going to be P sub C. And these will look something like this, right? Acting upwards. And we can look at the pressure that's being applied maybe outside. So in other words, we can just draw this free body diagram that we realize has these little bits of air out here as well, but we don't care about those because that's part of our free body. It doesn't weigh very much, just like the air inside this cabin doesn't weigh very much compared to the magnitudes of these pressures. And if we look at these pressure magnitudes, this would be the atmospheric pressure acting outside. And the other thing that controls this are, if you think, the magnitudes of the forces that would be applied in the aluminum fuselage that pull down against this. T and T. And so what we could do is we could resolve these forces and we'd get something that would look like this. So if we resolve upwards, the cabin pressure minus the atmospheric pressure multiplied by, and if I give some geometry to this, so it goes this amount into the page, and what am I going to call that? I'm going to call that L, and I'm going to call this diameter of the fuselage D. So the area that this acts on is L times D. And that has to be equal to the magnitudes of 2 times T. And if you think about what T is forces. And so those forces, this force is going to, so stress over area is equal to a force. So a force is equal to stress times area. And so if we had, for instance, the strength of this, if this is the strength of the steel, then we could replace this just as 2 times the strength. The area is going to be the thickness of the fuselage, which I'll call lowercase t. And it'll be multiplied through by its length, right? This is just an area. So this is the same as this. Stress times an area is a force, and the force is T. And so there we have enough to be able to solve it. So we could figure out, for instance, what we want to know, and if you're designing something, you'd probably want to know what thickness aluminum you'd want to apply. And so if we rearrange this for the things we know, length, diameter, and we divide, so this is not dividing through by this TL is just the area, and we divide through both sides by 2 times the strength times the length should be equal to thickness. And if we put some numbers in for what we know, we've already said what these are, so this is, so if we write in longhand, so it's going to be 100 minus 20 times 10 to the 3 newtons per meter squared, right? Because these are kilopascals. The length, I guess the lengths cancel out. The diameter is equal to, say, 10 meters, I think, something like that. Divide through by 2 times. Apparently the strength of aluminum is about 200 megapascals. So if that's right, I think that's right. And so if we look at what these are, then the thickness you need is hopefully going to work out. So this is newtons per meter squared as well. This is in terms of length. So this is the same as 80 times 10, which is 800, times 10 to the 3, over 200. I missed out a 2, right? 400 times 10 to the 6. And it's meters, and so T is something like 2 millimeters. 2 times 10 to the minus 3 meters. Sounds about right. Sounds like about a reasonable thickness for a skin on an aircraft. You know it's not a meter thick. You know it's not the thickness of foil, tin foil, and so 2 millimeters is about right. So we've kind of done some of the things that we've talked about here. We said we would do 3 things. How big are the forces? Well, we've defined forces here by multiplying pressures over areas, very simply. We haven't really figured out where they act, but we've resolved them vertically. We haven't needed to figure out where they act. If we looked at the geometry of this, we'd find out that the place where this big blue force would act would actually be right in the middle of the plane, through the center, but we don't know that yet on this thing. And we've kind of defined a failure mode that says that when the stress gets bigger than this strength, then it will fall apart. And so that's basically what we're attempting to do today. And so we'll use something that's a bit more sophisticated than that. But we'll do it in the same order, is that we'll try and work out a generic way in which we can figure out how big the forces are. And we'd like to be able to generically figure out exactly where they act. And then that's the first step in us being able to define, if you know the force is acting on a structure, you can figure out how it might fail. So you have to define the mode of failure to be able to go that next step. Okay? So that's our plan for today. So we'll try working on that first. How much comes off here? All right. So I'm going to, you can tell me if I go off the edge of the plot. For some reason I like red more than anything else. And so we'll talk about pressures on structures. Actually, okay, so I should know that this, anything on the other side of this isn't going to work out so well, just from this, on the projection, okay? And so let's take the example that we talked about for the dam. And so the idea for that is that, so you can imagine that you might have a structure that sits on a base. It's not a very good representation really of our arch dams that we talked about. And this structure would have some weight attached to it, just from the mass of concrete that's sitting on its back. And so the question would be that we know from what we've talked about so far that pressures change with depth. And at least for liquids, we know that pressure is equal to unit weight times z plus P0. If we start here at 0, then we can get rid of this term here. So we can kind of generically use this. Let's relax the assumption right now that this should be negative z. Just use it as positive for now. And just take that as being the case. Then, in the same way that we just drew a free body diagram for the plane fuselage, we can do the same thing here. And so, if we look at drawing this out so that it's a kind of a three-dimensional structure, we know that it will go into the page by some amount. This would be the width of the dam, etc. And also this pressure distribution would be going into the page as well. So you get the picture. And so what we could do is we'll just use a representation of this, where, as I say, we'll relax this requirement that z should be positive upwards for now. But what we're going to do is we're going to take the area of this particular structure, which I think I'm drawing very nicely here. Quite proud of myself. And if we call this some width across here, and we'll call this some increment dz, then the area of this piece here is just equal to the width times dz, which is just equal to an area, dA, I suppose, right? Change in area. And so what we'd like to do, if we want to get the magnitude, what we're after is the magnitude of the equivalent force, the resultant force that acts here, that is due to this distribution of fluid. That's all. And so the magnitude of this force, we can just write as being equal to the pressure multiplied by the area, the sum of it. It's not a very good sigma. The sum of incremental pressures times the area, and of course we can write that as an integral, and that integral should be from y0 to y1 at these points right here. Right? So I guess this would be y1 and this would be y0. So not y, z. We use y later, but let me just get rid of that. So between z0 and z1. And so if we put that in there, we can replace this. This would be z1 and z0. This would be going in here, and so it's an integral z0 to z1. The pressure multiplied by the width times dz. And we also know that the pressure we can write as this, and so this will be just the integral z1 z0. Pressure is equal to unit weight of fluid times, I'll put W here, times z dz, which is the same as the width times the unit weight times a half z squared evaluated between these two limits. And if I'm not belaboring the point too much, we have a final force which we can write out as a half. This is 0. Unit weight width times z1 squared, which is also the same as a half unit weight width times z1 times z1. And the utility of writing it that way is that this term here is actually the area. It's the area of this whole feature here. So if you like, area is equal to width times z1 minus z0, I guess, but we've set z0 as nothing, right? And so this is actually a standard result which we can use, and that's the force that acts on the system is equal to the unit weight of the fluid, the area of the plate, and multiplied by the depth of the centroid. So in this particular case, this is a half Z1 for us. But this is what we call the depth of the centroid. Of the area. So the area of the plate that we're interested in. And so the centroid, of course, is the balance point. So this is the plane that we have on the back of the dam. And so if we were to try and support that, if I, just like Pennsylvania, where State College is, equally inaccessible to all in the state, you take the state and you draw an X between the northwest and southeast corners, etc. That's where State College is. The centroid of the state is here. And the balance point, if you like, of this plate, which is representing the back of the dam, is this height of the centroid. And so, in other words, if we wanted to calculate the magnitude of the pressure, the force acting on this point, all we need to do is figure out exactly where the center of that plate was, which is here. And if we can get the depth of the fluid at this point, which is h sub c, which also happens to be a half of z1 here, the depth of this point will always give us the magnitude of the force that's acting on a plane surface. And you can kind of rationalize that must be so just by looking at the geometry of this. So if you take a plate which happens to be sitting below the water that's on an angle, then you can imagine that the pressure at the midpoint of this, I don't know why I want to use blue, so I don't know why it's not being blue. That pressure is equal to this h sub c. So the pressure here is equal to unit weight times h sub c, right? And so if we draw the pressure distribution on that figure, then this is higher up, and so the pressure here is less. This is lower down, so the pressure here will be more. And so we could draw a distribution of pressure on this figure that would look like this. We know that pressure is equal to unit weight times z. We know that z varies linearly on this as we go down. And so this distribution also has to be linear as well. And so if you think about what is physically going on here, is that at this point here, if you just drew the pressure as constant here, with this magnitude P is equal to unit weight times hc, which is this amount here, then all you need to do to be able to make this blue distribution into the green distribution is to take this triangle off here and put it here. They'll exactly balance each other. And so the physical reason why we can always get the mean pressure, average pressure that acts on a plate as being one which acts at the centroid is exactly that. A geometric explanation of it is exactly why that's the case. And so this expression here, although we did it specifically for a plate which was vertical, it was on the back of the dam, right? There's no reason why it can't be both an inclined plate at any inclination that we choose, horizontal included, like for the calculation for the comet, and there's no reason that it can't also be inclined and not cutting through the surface of the water. It can be at any depth, just from what we've shown here. Okay? So that's the first step in our journey. So this is absolutely always the case. So the unit weight of fluid, the area of the surface, that flat surface is acting on, and the depth of the centroid, the balance point of that of that plate or that area at a location. So in other words, if the plate was no longer rectangular at the back of the dam but had an edge off it, again, forget that I've folded that over, the balance point of this thing, the new balance point, that would be the new centroid of this plate's center area, and that would be the HC that you'd want to be able to use in this expression. And the expression will work in that mode. All right, so we've said something. So this really has been talking about the magnitude of the force. So this is number one, magnitude of force. Of, I guess, resultant. That's why we call it FR, it's the resultant. So the other thing that we could do, I guess if we were interested in this, is to come back to this figure. And so if we now know the magnitude of this force FR, then we could draw a free body diagram. And we'd be interested in knowing exactly where the resultant of these two forces would be. So let's call this Fx now, so we don't confuse it with what we're going to do. And the resultant force of these two forces is just Pythagoras, right? So if we wanted to define the resultant, we know that Fr squared, I guess I know I'm off the screen. We know that Fr squared is equal to Fx squared plus W squared. We're adding apples to apples. They're all forces, so we can do that. And typically we'd want to know what the resultant force is, and that would just be by taking the square root. So square root. And so that would give us the magnitude of more than one force. So if we can figure out what one of the forces is, which is this fluid pressure force, and there were some other forces acting on the system, then we might want to be able to figure out what those were. And so that's not just a useless exercise in itself, because you know that if you wanted to figure out whether the force Fr was big enough to be able to push this dam over, then really the arbiter of that would be whether the resultant force acts outside this point, allowing it to rotate, or whether it acts inside this point. If the resultant of W and Fr acts somewhere inside this point, the dam's not going anywhere. And if it acts somewhere outside this point, outside the toe, then like a domino, it'll just fall over. So that's one reason that we want to be able to know the magnitudes of the resultants. But now we want to know physically where it acts. For instance, we know that the weight of the dam is going to act through its center of mass, which would be, again, by taking this figure and dividing it in half, so it would actually act through this point here. We'd also like to know exactly where this force acts as well, because if we don't know that, then we can't resolve absolutely in space exactly where those forces act. So we said we wanted to do three main things. Magnitude of the force, done that. We've got an expression at the bottom of this page. We want to be able to take the resultants of that. That was the second one that we didn't include as our second term, but we've done that as this expression here. Third one is be able to calculate where they act. And so that's our next job, is to be able to figure out exactly where those forces would act. Okay? So I guess this is to talk about the point of action. So we'll use the same geometry that we had before. And so let's oops, I know I'm barely on the screen right there. Let's call this Y now, just because the book uses the same terminology, and it's useful for us to be able to do that. And if we go down here, we know that this is P is equal to gamma Y in this case. And we know that this is this pressure distribution that we had before. Again, we're going to have this geometry with the plate, if you like, that looks like this. It's again going to have some little incremental depth, which will be dy, y0, y1. It'll have some width attached to it. I guess this would be in the x direction on the surface. This little area here is going to be dA equals width times dy. And we're going to realize that what we could do, we could take it around any point, but specifically, if that's still on the screen barely, we could take a moment around this point. And what we'd like to do is be able to balance the moment that comes from this green distribution, incrementally defined, with the moment that comes from balancing this length here, which we'll call YR, and the force which we know how to get for that because we have an expression for that. And so what we can do is we can equate the moment around this point here, or it could be any point, it's just a convenient point to take at the top, with that due to the resultant force and the location where it acts. We don't know where it acts yet, but we'd like to be able to find that out. We'd like to know what YR is, but we can certainly get this moment by incrementally summing the moments around here, and we know this, and so if we do that, we can get YR. So that's our task. So what we can do is we can write the fact that the sum of the moments are equal to this force times the lever arm which it acts through, right? Big force represents the integrated effect of this green distribution multiplied by its unknown lever arm, has to be equal to the moment that is applied. And so we could just rewrite this as YR is equal to the moment divided by the force. And so then, if we want to get this, we have this from the previous page. We need to be able to figure out what the moment is. And so let's figure that out. So YR is equal to 1 over the force resultant times the moment. And so the moment is going to be equal to the force times its lever arm. The force for our particular case is going to be the pressure at a point multiplied by the area, which is W dy, right? So this term here is just an area times the pressure is a force. And the lever arm is going to be equal to this distance here, which is y. Whoops. And so if we write that out in longhand, so it'd be the summation, if you like, of the pressure times the width times dy times y. The pressure also we can define as something else, right? The unit weight of fluid times y. And so if we write this out, and instead of doing a summation of all these, we'll get a bit smarter between y0 and y1. Yep, these one here. And if we gather some terms, what's going to be there? The width is going to be there. The unit weight is going to be there. Y will go into here, and so we have y squared dy, I think. Hopefully that's what we have. And so if we do that integration, we end up with the width times the unit weight times a third y cubed evaluated between y0 and y1. If we take y0 at the top, we can just get rid of it. Let's assume it's 0 and keep this. And then if we do that, we have an expression, if we gather terms, which is 1 over this force, and it should be the width times the unit weight times a third, bless you, y1 cubed. That should be about it. So that's our expression that we have that defines our behavior. And so that's okay. So I guess we can note a couple of different things. One is that in the geometry that we have, I guess I'll put it on the screen so I know that's just going off the screen. If we look flat on at the geometry that we have of this plate, then we know a couple of things. We know in this particular case, if we look at the centroid of this plate, to get this point here, then this is equal to y1, this is equal to 0, this is equal to yc equals hc, kind of, right? If it's vertical, yc and hc are the same. We've chosen y, by the way, because we don't necessarily need to have the y-axis vertically downwards. The plate could be inclined, in which case the y would just be in the plane of the plate. So that's the reason why we've done that. So I guess we can see a couple of things. The one is that y1 is equal to 2 times yc, right? This. And so equally, y1 to the power 3 would be equal to 8 times yc to the power 3 as well. Just from the fact that this centroid is half this distance here. And so the reason for doing that is that we can write this out in longhand as the width times the unit weight divided by FR. FR is equal to the unit weight times the width times YC. So this is equal to, can I get them on the same page at the same time? Yeah, just. So this is going to be equal to the unit weight multiplied by the area, which is the width, times 2yc. Right, this there. And this is going to be equal to yc also, right? This is the depth of the centroid. So this whole term on the bottom is just equal to FR. And we have left on the top 1 over 3 y 1 cubed, which is equal to this. So let's separate that out. And so now, see if I can do this without messing it up. So we have width, unit weight. We have width, unit weight. We have 2yc squared. And we have 3 times y1 cubed, which is the same as 8yc cubed. So if we go through this and get rid of the terms that we don't need, how are we doing for time? We're doing okay for time. Get rid of the widths, get rid of the unit weights. We end up with the result that YR is equal to 8 over 6 times, what, well, got rid of this, times YC. Oh, that was actually quite easy. And that actually is the right result. I surprised myself. And which we could also write as being equal to, because of this relationship here, then it would also be equal to 4 over 6, which is the same as 4 over 3, YC. And if we account for this observation here, that YC is equal to 2 is equal to Y1 over 2, then we end up with the magnitude of 2 over 3 Y1. So that is not a standard result. We'll be able to convert it into a standard result next time, but it's a result that's specific for this specific geometry. And so if we come back to look at the geometry of our particular pressure distribution, right? This is our water surface. Whoops. No, you can't see that. This is the water surface. This is Y. This is the distribution. That's actually probably a result that you already know, actually. This is pressure with depth. This is pressure is equal to unit weight times the depth. If you look individually at the distribution of pressure here, a standard result for triangular distribution is that the point of action is F. Why does it do that? It shows blue, but it doesn't want to give blue. I want blue for water. Is that the magnitude of this force, this resultant, is Fr, and the location where it acts is YR, and it equals 2/3 of the height of this distribution. This is Y1. So that is absolutely a standard result for that particular geometry, but not a standard result, say, if the plane didn't start at the surface or didn't intersect the surface. It's not true. You can show that it's not true by just thinking about what the pressure distribution would look like if the surface was higher up. It would not be 0 at the top of this triangle, and therefore this doesn't occur. And it's not a standard result if the plane is inclined, but we can turn it into one quite easily. And so the point of all this is that really from the three things that we said we wanted to be able to do at the beginning of today, and I'll just go back to show them. We said we kind of wanted to do three things. We wanted to figure out how big these forces are. Fr, we know how to do it. We just integrate over an area. There are some standard results. And the standard result is that if we have an area or a plate that's in a fluid, and that we know where the balance point of that plate would be, the center of gravity of that plate, then that is the location below the surface that we can calculate the pressure at, and we can multiply the fluid pressure at that point by the area of the plate and the unit weight of fluid. Well, the pressure at the point multiplied by the area of the plate will give us the force on that plate, or the depth of that point below the surface multiplied by unit weight multiplied by the area of the plate will also give us Fr, right? Because we know that Fr is equal to hc gamma times area. And this term here obviously is just pressure at that point, centroid. And so we can get it either way, right? So we have a standard result that gives us the force that acts on a plate, any plate we have, any depth, any orientation, standard result. We know if we have other forces we can resolve them. We can calculate where they act if we take moments around it. We've done it only specifically for a particular geometry, which was for a plate that's vertical and that intersects the surface and therefore has this triangular distribution. And if we do that, then the location of the point of action as a standard result is 2/3 of the way down the plate. And of course, I'm never sure whether I should do this or whether it actually confuses people, is that what we have, I think it's kind of a nice demonstration, so you can draw your own conclusions about it. The magnitude of this 2/3 is, if you look at the pressure that's acting against this wall, is a triangular distribution. The 2/3 point down this is actually the balance point of a triangle around its point, so the centroid of a triangle. So in other words, in here somewhere, the centroid of this pressure distribution, it would be a third of the way up, it'd be a third of the way from the base, so it'd be around here. This is the point where the centroid of the pressure distribution is the location where the pressure acts through the system. And so I'm always hesitant to mention this because people get confused with the centroid of the plate, where you measure the depth below the surface to measure the force, Fr. But a physical representation, if you like, of this 2/3 depth to the standard result for triangular distribution is because it's the balance point for the pressure distribution. This pressure distribution of the point. So that's enough for today probably. We're 2 minutes early, but we'll leave it there. So next time we'll talk about making this into a more generic result so we can use the point of action of the force, but use it generically for any plane that we have below the surface, not intersecting the surface and inclined. Okay? See you Wednesday. Thank you.